Okay, now let's take a look at a new arena, which is the details behind atoms, isotopes, and ions. And this is going to be a fair amount of stuff you've seen before, but I want to make sure we establish the proper vocabulary for it and we're all on the same page what those means. So what we're working with is what's referred to as atomic theory, and as discussed, the word theory is a very powerful word. It means there's been extensive studies done by dozens of scientists, all which made predictions that were supported. So atomic theory is the base upon which we build this. There is a term, the term is called an element, and an element is made up of these small particles called atoms, and a atom cannot be divided into a smaller unit and still remain an atom. So an element is a collection of the same kind of atom. The atoms in that element will have identical mass, and they will behave in a similar way. So what makes an atom of one element different from another is an atom such as carbon will have a different mass and behave differently than an atom such as hydrogen. And therefore a collection of hydrogen atoms will behave differently than a collection of carbon. We are able to make atoms come together and hold together. When we do that, we make molecules or compounds, and when they do this, that compound will take on new properties. Now it's important to realize that you cannot add half an atom. You can't add half a carbon or half a hydrogen atom. So when you put things together, they have to be in whole numbers. The compound or molecule may have 1 carbon or 2 carbon or 3 carbons in it. It cannot have a 2.5 carbon. Now, when you have a chemical reaction occur, what happens is atoms separate from each other and they recombine into a new form. The atoms themselves don't get changed around. We are simply generating a new combination or arrangement of those atoms. Here's a periodic table. Most of you have seen this. It lists the atoms that exist in the universe. As you can see, there's approximately 103 atoms that have been identified. The last one is lawrencium. And these atoms are what make up all matter in the universe. That does not mean there's only 103 different kinds of matter. Instead, these atoms can be combined to make molecules or compounds, and in so doing, they become a new kind of substance, a new kind of material. And the number of combinations of this stuff you can make is ginormous. And so the different kinds of material that exist in the universe is almost limitless, but they're made from a limited amount of items to work with, which are the atoms that you see. Now, every given atom or element, remember an atom is a single item, an element is a collection of one kind of atom. So every element or atom has certain information about it that we need to know about. First, the atom that makes up the element has a certain number of protons. That number of protons is called the atomic number, and it's given the symbol Z. Now, for reasons we're going to find out, atoms don't all weigh the same, even though they're the same kind. For example, some iron atoms weigh 54, others weigh 56, others weigh 60. And so what happens is, because there are these different kinds of iron atoms, they have averaged them together to get an average mass. And that's called the atomic mass. And the reason why it's a decimal is because it's an average value. there always is a symbol assigned to it. Many of the symbols were assigned by Greeks as well as alchemists. Some of the names are based on Latin. So Fe in Latin, ferrous, means iron. So we will see symbols which don't connect directly to the name, but that's because of the naming took place many, many years ago. So how do we list the element symbols? First of all, the first letter is always capitalized, as you can see, the letter C, which stands for carbon. And the second or even the third letter is always lowercase. For example, if you see capital C, lowercase o, that stands for cobalt. What you never write is capital C, capital O, because the second letter must be lowercase. If you were to write capital C, capital O, you actually are representing a molecule of carbon and oxygen. So that's not the way to represent cobalt, but it is the way you represent that molecule. Mn is manganese. M lowercase capital N doesn't work because you don't use a capital N. Instead, use a lowercase. How about the atoms themselves? This is something you're familiar with from before. Atoms, it's the basic unit of an element, meaning a collection of atoms make up this thing called the element. There are times when atoms are able to combine. And here are what are called the diatomics. You need to memorize these. H2 means there are two hydrogens connected to each other. N2 means two nitrogens are connected to each other. You'll notice there are 7 different atoms that combine with themselves to make the diatomic. You will need to memorize these 7. Are these the only 7 elements that are able to do this? That is correct. For example, you never have C2, which would be carbon. You can't have 2 carbons connected to each other. Only these 7 can connect to themselves and be completed. Now, atoms can, of course, attach to themselves more than just in pairs. Those are referred to as polyatomics. For example, you can have 4 phosphorus atoms connected. You can have As, which is arsenic, connected to make 4. So polyatomic elements are elements where multiple identical atoms have combined with each other. So you have single atoms up top, you have diatomic elements, and you have polyatomic elements. Again, the diatomics you will want to memorize. This is what a diatomic would look like. We might suppose these are 2 fluorine atoms. You'll notice that there's 2 of them stuck together and held together very tightly. This is a diatomic. One might suggest it's fluorine. That's what a molecule would look like. 2 or more atoms connected to each other. Now, what makes up an atom? An atom is made up of what are referred to as subatomic particles. What are they? Well, they are protons, which have a positive charge, and they exist in the nucleus. Then there are neutrons. They also exist in the nucleus. And they're basically the same size and the same weight as a proton, but they have no charge. Then the outside are the electrons. Electrons are almost 2,000 times smaller than a proton or a neutron. So the electrons, oddly enough, still have as strong a charge as these large protons do, except the electrons are negative. And that's kind of interesting. So the size of a proton is much larger than the size of an electron. But the charge of the proton is equal to the same amount or strength of charge that the electron has. They're just positives or negatives. The combined proton-neutron combination represents the nucleus. So, what is the weight of a proton? Very small, 1.673 times 10 to the minus 24th. Neutron is ever so slightly bigger, and as you can tell, the electron weight is extremely small. So, here we see that we have an atom, and that atom has 25 protons in it. 25 protons means that it's manganese. I know that because I can look it up on the periodic table. Now, this particular manganese atom has 25 protons, and it has 30 neutrons. The 0 over the N means there's no charge. And there are 25 electrons. So notice the number of protons and the number of electrons is the same number. So the overall charge of this atom is 0. Do notice that the number of protons and the number of neutrons is not the same, and it doesn't have to be. Now, the nucleus contains almost all of the mass that's there. The electrons circle like in a cloud way outside. If we imagine putting the nucleus as a strawberry on the 50-yard line in the Wolverine stadium, how far out would the electron shell be, or electron cloud? The electron cloud would be in the parking lot. So notice how big of a gap there is between the nucleus and the outside cloud of the electrons. So the cloud takes up most of the volume, but the nucleus makes up most of the mass. Now let's talk more about the atomic number. The atomic number Z is the number of protons in the nucleus. The number of electrons in a neutral atom is also the same number of protons. Those charges cancel out. Do electrons and protons always have to have the same number of them? No. But if it's neutral, they match. But it's the number of protons that determines the identity of an element. Now, what that simply means is the number of protons, which is the atomic number, is what determines the kind of stuff you got. If you have an atom and the nucleus contains, for example, 25 protons, it's going to be manganese. If there are 6 protons, it's carbon. Yeah, but what if the number of electron changes? What if an electron leaves or an extra one is added? Does that change it from like a carbon to an oxygen or from an iron to a cobalt? No, it doesn't. When you switch electrons around, the actual atom itself fundamentally doesn't change. But the protons does determine it. So let's take a look here. What we notice in the top row is a long list of atoms. H is hydrogen. The number 1 means it has 1 protons. He is helium. It has 2 protons in it. Lithium has 3. Beryllium has 4. And you'll notice that we can string all of these atoms in a long row from 1 to 20, from hydrogen to calcium. If you do that, you'll notice there's an increase in the number of protons, one at a time. But other than that, no pattern seems to appear. But if you take this long list of atoms and you organize them into different rows and columns, suddenly a pattern does emerge. If you take a look at hydrogen, lithium, sodium, potassium, that's 1, 3, 11, and 19, that's all in the pink. It turns out that all of those atoms chemically behave very similar to each other. And the reason why is the valence shell number of electrons is the same. That first column, all of them lose 1 electron. The next column over, which is Be, beryllium, magnesium, calcium, they tend to lose 2 electrons. So if you organize this long list of atoms and organize them based upon similarity in terms of how they behave chemically, a pattern develops. That vertical column refers to the group of atoms together that behave so similar to each other. The horizontal are the periods. Now notice that atoms that are listed in the periods, you will notice that their atomic number, or number of protons, goes up one at a time. Lithium is 3, beryllium is 4, boron is 5. So left to right, the atomic number gets bigger and bigger. But if you look at it vertically, if you look at groups, what you see is not this pattern of a gradual increase in the number of protons. It kind of jumps. But what you do have is you do have groups of atoms that behave similar to each other chemically. And so horizontal is period, vertical is grouping. Periods, you see an increase in the number of protons. Grouping, they behave the same chemically. Now, because of this, very large clusters of atoms can be observed. What do we mean by that? Well, as you move down the periodic table, you have 7 periods. As you move across, you will notice there are 18 groups or 18 columns. There is often written in a different notation, 1A, 2A, then there's 3B, 4B, 5B. The distinction of the A versus the B, we will not discuss at this time, but we'll discuss it at a later time. So now watch what happens. You have now patterns within the periodic table. All of the columns from left to right, including the grouping down below, those are all called metals. Now, for example, look towards the middle. Fe, right in the middle of the periodic table, number 26. Well, that's a metal. Co, cobalt. Ni, that's nickel. We are familiar with those as metals. But it turns out that calcium, potassium, magnesium, lithium, those are on the left. They also behave like metals. What does that mean? All the atoms that are in yellow, they all lose electrons during chemical reactions. Since they all lose electrons, all of those atoms become positive ions. And because they lose the electrons, we call those metal ions. Now, if you look at the right, where the blue is, those in blue are called non-metal groups. They're non-metal because they always take on new electrons. And so the non-metals behave in a certain way where they gain electrons. They tend to become negative ions. What about that middle group there, where that red staircase is drawn? What are they all about? They're called the metalloids. I've always felt that would be the greatest name for a rock band, the metalloids. They appear in gray, and the reason they're called metalloids is that under certain conditions chemically, they will tend to lose electrons and behave like they're a metal. But that same element, if it's under a different situation, they tend to gain electrons, and therefore they sometimes behave like non-metals. So it possesses both types. Now, within the metals. Take a look at it again. Within the metals. Take a look. You have lithium, sodium, potassium, beryllium, magnesium, calcium. Those are on the left-hand side. All of those are metals, but they are more, they each have unique properties different from the other. What do you mean? Well, that first column with lithium, sodium, potassium, that's in red. All of those tend to lose electrons, that's true, but they only lose one. So they all only use one electron. Therefore, we call that group the alkali metals. The next group loses two. So those are called the alkali earth metals. Now these right here in the middle, they're called transition metals. Now where we're going is the chemical properties of the alkali metals are different from the chemical properties of the alkaline earth metals. But all the alkali metals have similar properties. And that's true for the transition metals. They tend to be easily melted. They tend to be pulled long into threads. So transition metals have their own properties to them. Over here, the green with fluorine, chlorine, that group is called the halogens. Now you need to know that you're expected to know these different regions. You're expected to be able to fill out a periodic table with these names on it. The purple, we talked about them, those are the noble gases. Down below, that group is called the lactinide series. And then finally you have the actinide series. So each of these groups have unique chemical properties based upon how they chemically behave. Let's talk about isotopes. What an isotope is it is atoms that have the same number of protons. As you can see by this example, there is one proton on the left, one proton in the middle, one proton on the right. Because the number of protons is the same for all of these, all three of these are called hydrogen. But you'll notice that each of these hydrogen atoms do have a difference. They have different number of neutrons represented by the white balls. So atoms which differ only in the number of neutrons present in the nucleus, those are called isotopes. So you're looking at three isotopes of hydrogen. They have the same atomic number or the same number of protons, but the mass number or number of neutrons is different. Now, I cannot tell the difference from one isotope to another because they chemically behave the same. But you might suspect different isotopes weigh different amounts because there's added neutrons in some of them. But we can't pick up on that. So chemically, they are the same. So on the left, that's hydrogen. But it's a certain name for this hydrogen isotope. It's called protium. The next one is also hydrogen, but it's a different isotope. It's called deuterium. And finally, the last one is called tritium. Again, it's hydrogen, but it's different in terms of the others. It's an isotope. Now, how do we deal with all these symbols and stuff? Well, in this example, we're going to represent X as the chemical symbol. Let's imagine you write down there the letter C for carbon, or Fe if it was iron. So X is where you write the chemical symbol. A is called the mass number. The mass number is the total number of protons and neutrons that are in that atom. Z, that's the atomic number. That's the number of protons only. So if I have the mass number, that's equal to the number of protons and the number of neutrons that are in the nucleus. That equation you need to know. So we have chemical symbol is X, mass number is A. Now let's take a look at some of these by example. The atom on the top is hydrogen. Now the number 1 on the bottom says that's the number of protons, it's 1. What's the total number of particles in the nucleus? 1. And we call it hydrogen dash 1 because there's only one item in the nucleus. Now this is also hydrogen, the middle one. You'll notice the number of protons is still 1, but there are 2 items in the nucleus. And we call that hydrogen 2 because there's 2 items in the nucleus. Quick statement. If you took away the electrons, those are the minus ones, if you took those away, none of the symbols would change. Because when you deal with isotopes, you deal with the symbolism, you don't actually deal with the number of electrons. These are the names of each of those type. So take a look at this. Sodium, Na, that's on top. There are 11 protons, and there are 12 neutrons, and there are 11 electrons for sodium. How would you write that symbolically? You'd write Na, 11 on the bottom, because there are 11 protons, 23 on top. Whoa, where'd you get 23? You simply add the number of neutrons and the number of protons together, and that will give you the mass number, which in this case is 23. Now skip down to silver, Ag. 47 protons, you got 62 neutrons, add that together, get you 109. That's sodium 23, notice the dash 23. And if you actually look at sodium, it looks like a very soft silvery metal. Silver, 109, that's an example of the silver. Charges. The charge on an atom determines its electric behavior. It's the basic idea behind all chemistry. If the number of protons is greater than the number of electrons, it will have a plus charge. If the number of protons is less than the number of electrons, it has a negative charge. So the charge on an atom is when you take the number of protons and you subtract the number of electrons. And that again is an idea you need to know. That when you take the difference between the number of protons and number of electrons, that will give you the charge. Now, to write it, you simply write the number and whether it's a plus charge or a minus charge. In this class, I will not take off points if you put the plus in front or the plus after. However, convention says put the plus after. So, we know the mass number is written in front, up top, atomic number, bottom on the front, and then the charge is written above. So, let's practice this. Write the isotopic symbol for an atom with 78 protons, 119 neutrons, and 75 electrons. Pause it right now and see if you can write it out. Here we go. Pt is, where is that? There it is. Pt is platinum. There are 78 protons. That's how I knew, and as you could tell, I was looking it up myself on the chart. Let's take a look. There are 78 protons, but there's only 75 electrons. There are 3 extra protons, so that's a plus 3. The total number of items in the nucleus is 197. So that's how you'd write it out. Ions. Ions are atoms or particles that have a net plus or minus charge. Ca plus 2. There's the charge. Notice you don't have to put the 1. You can have something called a polyatomic, in which several atoms are connected together and the overall structure has a charge to it, such as you see here, NH4, which is ammonium, and PO4 - 3 is phosphate. Positives are cations, negatives are anions. So there it is in sum. You need to recognize mass numbers, atomic numbers, charge numbers, the chemical symbol, and A is the mass number.